Fisheye objectives have proven very interesting for computer vision community with their ability to capture super wide field of view in a single shot. The perspective of gathering this amount of information makes such images highly interesting for scene understanding in various fields of application such as security, medical, or consumer electronics. However, to capture rays with a large angle of incidence, those systems are designed with a highly negative band first optical element that will induce a strong apparent distortion. This phenomenon leads to bent lines and a modification of object proportion, especially on the edges of the image. This spatially varying property makes it challenging to use fisheye images on learning-based approaches using convolutional neural network, as they do not respect the shift invariance principle. As removing distortion leads to pixel stretching and a crop in the field of view, our work focuses on studying the impact of different kinds of distortion on single-shot depth estimation. More precisely, we simulate 4 different wide-angle imaging systems, a linear fisheye, and 3 lenses with nonlinear distortion called panomorph lenses. Such systems, provided by Immervision, are designed with a controlled distortion function and an optimized sensor coverage to increase the pixel density on a region of interest, respectively the center, the median zone, and the edges of the image. We can observe here the different rendering that can be explained with the curve on the right showing the relative pixel density across the field of view compared to the linear fisheye represented with the blue line. We used 1 linear fisheye and 2 panomorph lenses for the first experiments. We created a dataset of images for each system by wrapping multiple 3D panoramic images using this distortion function. As all of them increase the pixel density from the center to the edges of the image, we can notice the nonlinearity for the panomorph lenses in orange and green. In this way, we can simulate images with 180 degrees of field of view with different regions highlighted. We then use this dataset to train 3 different networks with the same architecture borrowed from UNL, a 4-block network composed of squeeze net, multi-scale feature extraction deconvolution layers, a fusion block, and AlexNet for the final depth reconstruction. For the training, we use weighted sum of 3 different losses still borrowed from UNL, a pixel-wise log error on depth to get an accurate depth map, and 2 losses that evaluate the error along the image direction at different scale for a more accurate edges reconstruction. We used Adam Optimizer and trained for 1,200 epochs each network. At Inference time, we compute the median relative error for each pixel to obtain those error maps. Each ring represents 10 degrees of field of view, and the red circles indicate the area of increased resolution. We calculate the median value of this error for each section of the field of view and obtain those results. As we can observe, as all networks perform the best at the edges of the image where the pixel density is the most important, the best results at the center are obtained with the network trained with a center augmented resolution system indicated by the arrow. The same trend is observed on the edges. Then, to better represent the optical system, we realized the second experiment to simulate possible variation in the distortion function due to manufacturing tolerances. Taking a median augmented lens as an example, we use its nominal distortion function and we randomly generate 20 functions using tolerances and Monte Carlo. We created a first simple dataset using the nominal function and trained the network in the same condition as before. Then a second network was trained. At each iteration, the warping was performed by randomly picking one of the 20 generated functions to create a tolerance dataset. Both networks were then compared and tested on a tolerance test dataset at inference time. We can observe that best accuracy is obtained in the area of increased pixel density for both networks within the red square. And even if the network trained with varying distortion performs better, both networks are robust to manufacturing tolerances. In the end, we showed that by countering nonlinear distortion, it is possible to increase neural network accuracy in an area of interest compared to performances obtained with linear fisheyes. We can then locally get closer to results obtained on narrow angle images while keeping acceptable depth estimation on the entire 180 degrees field of view. For a given application with a specific area of interest, it could then be possible to identify the ideal distortion function for optimized performances. This could constitute specification for optical designers. In future works, we would like to explore other learning-based applications such as object identification and other network architectures to confirm our results. Increasing the resolution of input images and testing real images is also a direction we would like to investigate. Thank you for your attention.